Good evening, people. Today I'm starting a new series. We'll be going through different research papers in the genre of artificial intelligence, and throughout the history, all the research papers that have been written in this domain, and also in the domain of high performance computing, because our AI requires high performance computing for model training and so on. So both are really important. Both are yin and yang of large language models and so on. So today the paper and the topic that we'll be focusing on is skipless under concurrency, and we'll be going through how skipless work under a serial program, like when there is no concurrency. Then we'll talk about what a concurrency is and how to handle and tackle concurrency, and then we'll go towards uh, trying to build a skip list which can handle concurrency. And why is skip list important, and why is skip list with concurrency important, and what are the applications in which this can fit, and what kind of application are we trying to achieve with skip list in concurrency. So let's get started. So what is a skip list? So a skip list is a probabilistic data structure. What do we mean by that? So in general, if you create a data structure, if you have an idea of a data structure, then you're sure about its time complexity, right? That this is the way it will work for sure. But a probabilistic data structure is a data structure which whose functionality is based upon a probability that okay, if we scale this data structure to this level, then this is the probability with which this particular time complexity will hold. So, for example, uh, in the case of skip list, if we have a skip list, we can say with a certain probability that it will have an order of log n for insertion, for example. Okay, in the worst case, it can go to order of n, but the probability is so low that it almost never happens, and we can calculate that probability and the certainty with which we can tell that okay, this will be the time complexity of this data structure. And why a skip list over some of the other data structures is crucial. We'll talk about that. But let's first get into how we can create a skip list and what it is actually. So let's say that we have a linked list. Okay, and we have some data. One, two, three, four, five, right? And let's say we want to find three. Okay. Now, because it is a linked list, in a linked list, this data can be, let's say this is our hard disk. Okay. Then this one can be present over here in, let's say, this address location is, let's say, A. Then this two can be present over here in address location B. This can be present over here, C. This can be present over here, D. And this can be present over here, 5. Can be present over here, right? And all of these are connected through these pointers, right? These pointers are connecting these. So now we can't directly access the any memory. Like if let's say we know the index of 3 of C, we can't directly access it because we only have this particular node, which we call as head. Head is pointing to the first, uh, to the head of the to the head of the linked list. So to access this, we must go through this pipeline, right? So we can't do a binary search on this, right? On a linked list. So okay, fine. Let's take a array then, right? So let's say we have an array 2, 4, 6, 7, and let's say 9. Okay. Now in this case, let's say we are searching for 8, right? We are searching for 8. Then let's say we go to the middle point, and in this particular array, it is in the memory structure in our data in a hard disk in our RAM. This is stored like this, tuck, 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 throughout, right, sequentially. So if we know the address of the first element, and if we know the index of, let's say, the third value with respect to the first, which is 3, then we can directly access this. No need to go through this and then this and then this. We can directly access it. So now let's say we want to search for 8. We can just go to the middle element and see, using the um, using this idea that a sorted array, the next the let's say we are at 6. All the elements to the right of this will be greater than this. All the elements to the left of this will be smaller than this. Using this principle, we can compare our finding element to the current element and see, do we have to go to the left or do we have to go to the right. If the element that we are trying to find is greater than the current element, then we go to the right, and we don't check half of the element. We reject half of the elements, right? So at each step, half of the elements get rejected, right? So if you have, let's say, n elements and you want to reach one, and at each step, half of the elements get rejected, then n becomes n by 2, and then the search space becomes n by 4, and then the search space becomes n by 8, and so on. And after log n steps, it will become 1. And the one element that we are trying to find, right? Now, you say, okay, so we can do a binary search on this. So the searching is really fast in an array. So let's use an array. But the problem with an array is, let's say that we are trying to insert 8 into this array. Then in that case, we'll have to shift all the elements right of it, right? We'll have to break it apart from here. We'll have to remove all of the element from over here, insert 8, and then get all the element back, right? So we might, in the worst case, have to shift n by 2 elements, right? Let's say we are trying to fit it in the middle. Then we'll have to remove all the element either present to the left or to the right of it, and then insert all of those elements back. So it might take order of n. This is basically order of n. So an insertion will be order of n. But that is a benefit in the linked list. If we want to just insert an element in the linked list, then we can just insert it over here, right? But obviously, if we want to insert it somewhere in between, then that will be a problem again. So what is the solution? So one of the solution is a self-balancing binary tree, right? I won't go very deep into this. It'll take it'll become a 3-hour video if I just go and describe you this. But what this does is that it is a tree structure where the height of the tree is at max log n because of certain properties that the tree holds. And because the height is log n, you start at the root of the tree, and in the worst case, you'll have to only search through log n elements till you find your value, or you find this about the value that it does not exist in the tree in your search space, right? And then for an insertion, the maximum operation that you'll have to do is also log n, and for deletion, it is log n. So it works in log n for insert, delete, search. But what is the problem with this? And why is a skip list better in certain situations? Now, because of the way a self-balancing binary tree is structured, there are a lot of operations that needs to be done, right? And if we are doing multi-threaded programming or concurrent programming, okay, then a lot of threads would be working on the same self-balancing binary tree, right? And one of the trees might have rotated some element like this, and then one of the other thread uh, might get messed up for the other thread, right? So the amount of balancing and amount of complexity that gets involved in writing a multi-threaded uh, code for a self-balancing binary tree is very complicated. So this is where a skip list shines, because the way it is built is very simple for a multi-threaded programming, and it has certain properties which enable it to give us the time complexity with very, very, very high certainty of log n for insert, delete, and search. So let's look into how a binary search tree, a skip list is built. First, we'll go through the normal skip list, and then we'll go through how we can make it work in concurrency. So now let's create a skip list. So just like a linked list, by the way, a skip list is based on linked list, not arrays. So just like, wait, I'll create a little bit. So just like we create a linked list, we'll create all the values for our linked list, for our skip list. So this is level 0 of a skip list. So we'll just create one more element, and let's give it some value. So let's say this is 2, 4, 5, 8, and 9, let's say. Okay. Now, to go to any particular element, let's say we are searching for 8, then we'll have to, and we have a head pointer, right? Just like a linked list, we have a head pointer for a skip list as well. So this head only points to this first element, right? So we'll have to go through this and then this and then this, and then only we can find 8. And we can compare at each level and then we can find 8. But what a skip list does is, let's say, so this is our level 0, right? Or level 1, let's say. If we create another level and we only create elements at half of those elements. So for example, we let's say create another level and a value for 2 in this level 2. Okay. And then for 5 as well on level 2. Okay. And at 9, let's say. Okay. Okay. And let's create another level 3. If we create, let's say, a level 3 on level 2 and on, let's say, level 5. Okay. Now, let's say we have to search for 8. What do we do? We can, we are at head, right? Obviously. So when we start from the head and while creating our skip list, we maintain a value which tells us the highest level that we have in our skip list. So the level of this skip list, I'll just write it over here. Level for the skip list will be 3 in this case. Okay. So whenever we start from the head and we start from the maximum level of the skip list. By the way, one very important thing, in the practical implementation, while we are initializing the skip list, the head points to an element which is before the first element, and this is minus infinity, and there's another element which we keep as plus infinity. Okay, while we are initializing our skip list, and this node's height is max level, right? No, no element can have a level higher than this. So let's say we are going to have, let's say, 1,000 elements. Let's say, for example, we are going to insert 1,000 elements. This is our prediction. Then our level will be 10. Why? Because 2 to the power of 10 is 1024. So if our level is 10, then we will be able to incorporate 1024 elements, and definitely 1,000 is under 1024. So, and over here as well, this first node's height is as well max level, which is based on the prediction that how many elements do we want to insert in our skip list. So this is just there, right? Initialized like this, and at each level, initially it points to the node at over here. Okay, so this also has nodes over here, and this also has nodes over here. And each node of the minus infinity node points to the same level node of plus infinity node. Initially, this is not there. All this is not there. So this is pointing to this. This is pointing to this. This is pointing to this. I know it has gotten really messy. I'm sorry about that, but I just thought that that is something important to mention while doing a practical implementation. Okay. Now we start from the highest level of the first node, right? So we are over here. We are over here. And then these are the slow lines. And this is Rajdhani Express. Okay, these lanes are Rajdhani Express or metro or like super bullet trains. Why am I calling that? Because and these are connected as well. Okay, so the benefit of this kind of structure is if let's say you have to go to 8, you have to go like this, right? Like this. But in this particular structure, let's say we are searching for 8, then and we're starting from over here, then we can just hop on this line, right? We can just hop on this line, which is way faster. Why is it faster? Because it has fewer elements. It skips a lot of elements, right? It skips a lot of elements, right? So that is why it is faster. We can just hop from till the point which is lesser than the value we are searching for. So we are searching for 8. So we can just hop from this to this and see if the current element is less than 8. Yes, it is less. So we'll go to the next element. But this is currently pointing to null, right? So if it is null, then we just stop over here. Then we go down. So I'll just take another color. So let's just remove this. So we went from here to here, and then we went from here to here, down, right? And then again we'll hop. We went over here, and then we saw that this particular value is greater than 8. So we won't go over here. Rather, we'll just go down. So we went down, and then we went to the next, and we found our element 8. Okay, so this was our path, right? And because of using these fast lanes, we were able to skip lost a lot of the elements. So we didn't have to compare it with 4, for example, right? And if you can see if it is on a massive scale, let's say there are a million data points, then you'll be skipping through a lot of data points. So this is why a skip list is so fast. Now, the best thing about a skip list is its implementation, right? In concurrency. But first, we'll go through the implementation of a skip list um, in a sequential program. So I'll just keep it over here for your understanding, for a better understanding, and we'll just go through the implementation in C++. So let's start with the main function as always. We over here are creating a variable for the class type skip list, and then we insert these 5 values. Okay, so now we'll be going through the implementation of these insert. But before that, let me just show you the class implementation and the node implementation. Okay, so the class implementation is we have a head over here, just like this. We have a head of the whole skip list, and then we have the level. This is the maximum level of this skip list that has been achieved. So for this particular skip list, the maximum level is 3, right? And one more thing, by the way, I thought that I should mention it before going to the code. How do we decide while inserting an element that how tall will it be? How many levels till will this particular node go to? So what do we do is we flip a coin. Okay, we flip a coin till we get a tail. Okay, so if let's say we got a head, which so what is the probability of getting a head for the first time? 1 by 2. Okay, what is the probability of getting a head second time? 1 by 4. 1 by 4, then 1 by 8, then 1 by 16, right? So if we flip, let's say 8 coins, right? Then number of points which will be on the first level will be obviously 8. coin will be on the first level, but only half of the coins will be able to reach till this. Only half of the coins will be able to reach head on the first toss. So only half of the coins will be uh, in the second level. And then only one-fourth of the coins will be able to reach head twice. So only one-fourth of the coins will be on the third level. Only one-eighth of the coin will be able to reach heads three times. Tuck, 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 heads, heads, heads. So only one-eighth of the coins will be on the level 4, and so on. So, okay, so this coin toss decides what will be the height of a particular value slash node in the skip list. So now let's come over here. So these are the two values basically in the skip list, and then let's go to the node. A node has a data, like I showed you over here, has this data, and it has a vector of next, and this next stores the pointer to the next elements. So next for data 2, this particular node at its 0th index, or let's say at its second index, will store which node is it pointing to, which node comes next in level 2. Let me rephrase that. So the next vector or array of data 2 at index 2 will be storing the pointer to the value that will be coming next at level 2, at level 2 on this level. So 5. Okay, so this will be storing the pointer to this. That is why this is pointing over here. At level 3, this whole thing is vector, next vector. This whole thing is next vector that you see over here. This. Okay, this next holds node pointer to the node of the next value it points to at that particular level. Okay. So let's get over here. And then this is how we initialize a node. So the moment we create a node with a data and a level, then it initializes that node with the data and the level with, and obviously we have to resize the next array, right? Next vector. So we resize it to level +1. Whatever level we have currently of the skip list, we +1, and we initialize it with that. And we initialize all the pointers in the vector as null pointer. Initially, it is not pointing to any node. Okay, now let's go through the code of insertion, deletion, search, and if we want to print the whole skip list. So while inserting, the first is we initialize new level. This is the level of the particular node that we want to insert. And we go through a loop. This loop is basically the coin toss. So this rand generates a number, and if it is odd, then you increment the new level. So this has probability 50-50. Probability of tossing a coin has also probability 50-50. So it is basically like tossing a coin. If the current level of the skip list is less than this new level of this particular coin, then we need to resize and change the level of our skip list, right? So if the level is smaller, the current level of the skip list is smaller than the level of the new node, then if we resize the vector size of head, we have to first do that new level +1, and then we also change the value of that level of the skip list. Then we create a current pointer. So this current pointer is basically currently held, and then this is the pointer that travels through like this. Okay, so this will be the pointer that goes through like this. And we also have to keep an update pointer. So what this does is, the moment we are going like this, at each level, update holds the value of the node at that particular level through which we reached a particular node. So let's say uh, at level 3, this is the this is the node at which we went down, right? And now we won't go any further this direction. So update, I'll just create update over here. Update, right? Update at this level will hold the value of 5, the pointer of 5 basically. And at this level, it won't hold anything because it is going down, right? At this level, it will hold the value of this pointer, right? So again, it will be 5, right? So in this particular case, it was same, but there might be a situation where it goes something like this, then like this, then like this. Then the update will be like this. Then the update will hold this value over here, and then this value over here, and then this value over here, and then this value over here, right? This is what update holds. And why is this required? We'll find out later. Now we go from level to 0. So we start from the top and then we go to the bottom just like this. And at each level, we go to the maximum right that we can till we don't find a null or our value doesn't go over the value that we are trying to find. So if current next is not is equal to null and current next data is less than the data that we are trying to find, we loop. Okay, and we go to the rightmost for this particular level, and then we put the value that we are at in the update. Okay, so the moment we go down, just before that, the value that we are at, the value of the current, we put it in the update. Then we move the current to, after doing this, after going like this, we just move the current. So now the current can never point to greater than or equal to the value that we are trying to find, right? Current will always point to value less than the value that we are trying to find, because we only go to the next element if it is less than the data. So it will be pointing to this, right? 5 if we are searching for 8. Then we just move current equal to current next. So we go move current to this value. Now, if current is equal to null pointer, if that value does not exist, let's say we are searching for 10, then in that case, the next of this 9 won't be there, right? So it will be null pointer. So if it is null pointer or current data is not equal to data, so the data that it is pointing to, so let's say we were searching for, let's say 7. In that case, it would have came till here, and then the value that it was pointing to, which will be 8, would not have been equal to 7, right? So in either of the two case, element already exists, right? Element already exists. If it doesn't exist, then we'll create a new node with data and level that we just found out. And then we do this loop. And this loop is a very crucial loop. This loop builds back all the connections and updates the whole uh, skip list. What this does is, starting from 0, we'll go till the new level, and at each level, we'll create the new joins. What is the first join? New node next I is equal to update I next I. What this is new node. Let's say we have to insert. Let's say we have to insert 7. Okay, so we want to insert 7 over here. Then 7, and it has a level of, let's say 2, for example. Okay, it has a level of 2. I'll just erase this part. Okay, then at each level, starting from 0, new node next. So what next of this will be update I next. So update I, whatever value update had, the next value update had at that particular level will be given to 7's next. The 7's next will be pointing to this, because before this, update was pointing to this. So now 7 will be pointing to this. Just like that, 5 will be pointing to this. right? Because update was pointing to this before, right? And update I next is equal to new node. Update I is what? Update I is this, right? Update I is this. So for example, update level 3 is this, update 2 is this, update 1 is this, right? So these values will be pointing to nodes value. Update I next is equal to new node. Update I next, update 3 next is new node. Update 3 2 is new node, right? So this is what it is. And then if we were able to find it, not find it, then we inserted it successfully, else element already exists. So this is insert. Let's go through remove. Remove is also similar. We obviously initialize our current with head, and then we create an update array. There's a little bit of difference in this one. We start from the top, and then just like before, we go till 5. So let's say we want to delete 7, for example. Then we go till 5 like this. Okay, we go till 5, and then we at each level we put the value in the update. Whatever value we have at current, we put it in the update. Okay, and then we just move current to this, because current always points to a value lesser than the value we are searching for. So we just put current to this. So current becomes 7. If current is not equal to null pointer, if it is null pointer, then the value is already deleted, right? And current data is equal to data. So current's data is the data that we want to delete. It's not okay. Then we obviously start again with from the bottom level, and we go to the topmost level. Update I next I is not is equal to current. If update I is this, next I is not is equal to current. The if the pointer from over here to the next is not current, then obviously we have to break, right? Because that can't happen. If update I next I is equal to current next I, update I next I, so it will now be pointing to this rather than 7. It will be pointing to this. Why? Because update I next is equal to current's next. So current's next is 7's next is 8. So 5's next will become 7's next, and whole this whole node will be gone, because there is no node which will be pointing to this. Then we can just delete the current, this object, and then we have to also decrement the level in case there is not any value at that level. So what we do is we run a loop, okay, and okay. So what we do is, after deleting this node, this whole thing is gone, right? This whole thing is gone. We see if the pointer at this particular level, which particular level, the height of the node that we are deleting, okay, if it points, if that if the pointer at that level in the head node points to a null pointer, which means it doesn't point to any of these elements, then then that level can be removed. So we just decrement that particular level, and we say deleted successfully. For search also, it is very simple. We start from the head, and then we loop till we are less than that particular value that we're trying to find. And then if the value is found, just like this, if the current is not equal to null, or if the current data is equal to data, the value is found, we just print that the value is found. So this is it for a skip list without concurrency. Now, the great thing about a skip list is that you will see that the building of the skip list, or even the deletion of and so on, is requires very less operations. We just are reading for the most of the time, and while deleting, it requires very few changes to the pointers, right? It actually required just two changes to the pointer, uh, and that's it. So that is the main benefit of this, and now we'll be going through the code for a skip list in a concurrency. So now we'll be going through a skip list version which is concurrent, and there are two ways to implement this. Uh, First one is obviously using logs, but the problem with logs is that it debars all the other threads from accessing a major chunk of the skip list, so that reduces the efficiency by a big margin. So rather we'll be going through the log version first, but then we'll be going to the log-free version and its implementation in code and why it is way better. So let's go to the log version. So let's say that we want to, let's say, delete, I'll just wait. Let's say we want to delete 8, let's say, for example. Okay. Okay. We want to delete 8. I'll just remove 7. Yeah. So we want to delete 8. So the first thread that will be going to do this task, that will be on the mission to do this task, it will come over here, and it will go over here, and then it will go over here, then it will go over here, right? And then it will check if 8 is present or not as the next element to 5. If it is present, then it will do the delete operation. What will be the delete operation? Taking this particular pointer to over here directly and going through the update vector and using this to connect all these directly, right? Because the whole vector of 8 will be gone. So if this will be gone, then we'll have to connect this like this, right? So we'll have to be doing that. So as you can see, this whole region will be affected, right? The the pointer, the current pointer, the pointer just before 8, the element that we want to delete, starting from there till this particular the the column or the node just after the point, the value that we want to delete. So these three columns will be affected. So we can just, the moment we want to start doing these operations of changing the pointers, we can lock it, right? So we can log this particular node, we can log this particular node, and we can log this particular node and any operation that we are doing on them, and that's it. But the problem is that if we lock it, then if let's say a particular element, a particular operation is there to let's say insert an element after 9, let's say over here 10, then it is blocked, right? It is blocked till the time it gets deleted, right? Because this other thread can't go into 5, and to reach 10 you must go through 5, right? So it will be blocked to do an insert operation. So that is the problem. That is a big problem. So how can we do a lock-free implementation of this? In the lock-free implementation, the moment we are doing a swap or a change of pointers, that operation is only atomic. And with atomic, we mean there can be only this state or this state, no state in between, not a third state. Okay. So those particular operations are only atomic. And while that is happening, no other thread can enter that particular operation. Okay. Just for that particular time. Else, everything goes as it should be. So let's see how we can do this one. Now we'll be focusing on the coding part of concurrent skip list. So let's start with find. So I'm going through the reference material of a great book on concurrency programming called The Art of Multi-Core Programming or Multi-Thread Programming. So let's first go through the find method of the concurrent skip list. The node and the skip list class structure is the same as it was in non-concurrent example. So this time we'll be going through the concurrent example, but the structure remains the same. So the find method, as you can see over here, I'll just open this as well. Um, Yeah, so the find method takes uh, basically we're trying to find whether an element exists or not. And while doing that, we also fill up our predecessor vector and successor vector or array. And what does the predecessor and successor array contain? While we are trying to find an element, whichever elements we went through, whichever elements we went through, those elements will keep in the predecessor, and the next element, whichever elements we went through, will be put in the successor array. And we need these two values, predecessor values and successor values, while finding an element, because while trying to delete an element, we need these two arrays so that when this middle element is gone, we can connect these two predecessor element with the successor element. And even while trying to insert a new element, we need these two so that we can snap the direct connection and connect it to the middle one, and then from the middle one to the successor one. So we need these two arrays. So first we initialize the bottom level as 0. This is obviously. And then what this is, int key is equal to x dot hash code. So many times the data that we want to store in a that we want to store is not a number. It is some, it can be any kind of data, right? Any kind of data, any kind of object. So what we do is we find a hash code of that data, and then that number, that hash code can be sorted, right? Because it is a number, so it can be arranged in a sorted manner, in an orderly fashion. So that helps us to search these data in order of log n. So what we do is we find the key, we generate a key for that object. So whatever x is, whatever we are trying to find, x is the object, and we create a key, and then we try to find the key in our skip list. So we also create and have an array called marked. What this does is, we in the lock-free concurrency implementation, concurrency skip list implementation, what we try to do is, because we are not locking any region, while let's say we are trying to delete an element. Okay, while we are trying to, let's say there are multiple elements and we are trying to delete this element. Okay, then if a particular thread is trying to delete this element, let's say trying to uh, create new pointers from the predecessor to the successor, there might be another thread which might be in this same element trying to do something else, maybe trying to traverse to the next element, right? So while all the connections are not removed, we can't say that this element is removed from the skip list, right? So we keep the element in the array, in the skip list, and we just mark those connections as, okay, this connection is lost, this connection is lost, this connection is lost. And the moment the last connection is lost, we mark the last connection as lost. We mark the whole element as disconnected. So rather than breaking apart the connections, what we do in a lock-free implementation is we just mark those connections as deleted rather than physically deleting them. So this comes handy to keep a track of that. Boolean snip. Snip is basically changing the connection. So changing the connection from predecessor to the current element to the next element rather than changing it from predecessor to successor. So we now have few variables: predecessor, current, successor. Retry. What this retry is basically the moment let this code runs, then it takes the counter, the processor counter to over here. So if this runs retry, then it goes to over here. Okay. So what this is doing is basically, if some problem happens, if we can't do snip, if snip is false, okay, if we can't find the next element, then do it again, because some other thread might have altered that, right? So if some altercations happen because of some other thread, and snip wasn't possible, basically changing, going to the next element wasn't possible, then you retry it again. And what's in that retry? An infinite loop. And this infinite loop only breaks when we break it inside the loop specifically. So it breaks only over here if this happens. So this, and it is very common in log-free implementation of concurrency algorithms, because we have to keep trying certain thing till we get a chance to do it right in a log-free implementation, because uh, some other thread might be doing something on that node. So pred is equal to head at the start, and we start from the max level. So we are at the top of the first element in the skip list. What we do is current is equal to pred dot next level dot get reference. What this line does is get reference is basically every single element, every single node. Actually, if you see, I'll just go a little above. Every element of log-free skip list in Java, this is in Java implementation, is an atomic markable reference. So every node is wrapped around this atomic markable reference. What this does is that, first of all, it makes operation on this node as atomic, means either it will be 0 or 1. If it is this or it is this, it can't be in between. And secondly, you can mark it. Rather than deleting it, you can mark it that, okay, I'm marking it for deletion. So it comes with that. So every node in this particular implementation is a atomic markable reference. Okay. So current is predecessor dot next at that particular level, whatever, and get reference is basically give me the reference of the next element, but don't give me whether it is marked or not. It gives just the reference. It has two aspects, right? Every node has two aspects: the node itself and whether it is marked or not. So if you just call this dot get reference method, it just gives you the reference. It doesn't give you the whether it is marked or not. So you get that and you put it in the current, and then again you do an infinite loop. Successor is equal to current dot next dot level dot get marked. So it also finds the next element to the current, and this time it finds the next element, the reference, and whether it is marked or not. And it saves the marked, whatever value it gets for the marked, in marked 0th position. So in this marked array, it saves this value, whatever it gets from this, in the 0th index. So let's say the next element is marked. Okay, the successor is marked. Let's say successor is marked. Then marked 0 will be true. So while it is true, while it is marked, you keep doing this. Keep doing what? Keep moving forward. Okay. Keep making current as the next and successor as the next to the current. Keep going forward. Why? Because it might be that the next 10 elements are marked for deletion. So we can't do anything for those particular elements which is marked for deletion, right? Let's say we are over here right now, and the next 10 elements are marked for deletion, and then we have to delete the 11th element. Then we can't go to this one, right? We must go forward till we reach a node which is not marked for deletion, and then only we can uh, go down, right? Else we just have to go forward. So while it is marked, the next element, snip is equal to pred.next. Fill pred.next with current, value of current, if the pred.next is sucks. It means that first check what is the value of pred.next. If it is succ, then replace it with curr. Okay, and then these two, false and false, it is basically, if it is false right now, then make it false. What is the value of the marked variable, and what I want the value of the marked variable to be, what it was and what I want it to be. This is what it is. What is the value of the reference? What I want the value of the reference to be. Sorry, what I want the value of reference to be and what it was. If not snip, what this means is, let's say that this condition was not true. Pred.next was not is equal to curve. then you have to retry. Then some other thread messed up, some altercation was there, and you have to start from retry from line 113. Okay, and else if everything went smoothly, then you have to go to the next element, then the next element, then the next element, till you find an element which is not marked. And what do we mean by marked? We mean by marked is that whether we have marked it for deletion or not. If cur.key, and we do this, and at the last, if the value of the current element is less than the key, then wait, key has become more than, yeah. So if it has gone past the value that we are trying to find, then pred is equal to cur is equal to sus. Else you just break. Okay. So if our value is still less than the value that we are trying to find, we just go to the next element. We just keep going to the next element. Okay. Else we break. By the way, just a second. So what this is doing and what this is doing are two little different things. So this is making us move forward in the same level, while this is just checking again and again, is the next value available? Is the next value available? Is the next value available? Is the next value not marked? Till it is marked, it will just keep checking, is the next value available or not marked? Okay, just the next value. It won't make the cur and the SUCC move forward, while this makes it move forward. And at last, we put the value of pred and cur in the respective arrays for some other operation like deletion or insertion. So this is part of insertion or deletion. We need to fill these two arrays while doing insertion or deletion. So at the start of the insertion or deletion method, we call find and we fill these two arrays so that we can use it later in those functions. Let's go to add. Yeah. So what is happening over here is the top level is obviously a random level. What should be the level of the node that we are trying to insert, and bottom level is 0, and we create these two arrays, initialize it with something random. While it is true, do this again and again. Found, see, so found is basically were we successfully able to fill those two arrays and find x. If we were able to find x, it will be true. If found is true, return false. So if that element already exists, then return false, and we don't need to add that element. Else, if it was false, if the element doesn't exist, then you create a new node with the value x, and its height will be top level. And you start from the top and go to till the top, and you just put this. So whatever was in the successor array at that level, you just put it in this SUCC, and new node dot next at that particular level, new node dot next at that particular level will be pointing to the success SUCC, and you initialize SUCC this particular marked value as false, right? You initialize it as false. So this particular node we are trying to add, and you go level up, and this will be pointing to this. So this reference will be SUCC, and we'll mark it as false, that no, this node is not yet marked for deletion. Then we'll keep the value in pred and SUCC from the two arrays for the most bottom level, for the last most bottomest level. And then again, we set the value of new node.next as the SUCC. So you might think that, why, if we are going from bottom level till top level, and then again we are setting it in the bottom level, over here also we are setting it in the bottom level. So it is just for, extra check. That's it. It is. And also, when you're starting from the bottom level and you're going till the top level, in the meanwhile, it might happen that some other thread might have manipulated something. So you are again checking for the most bottomest level, and you're explicitly setting it again to SUCC, because while starting from bottomest to the topmost level, this value might have changed. So you are again cross-checking. Now, if thread dot next bottom level, so the next value or at thread is not SUCC. If it is SUCC, you make it new node. So if at the most bottomest level, if the next is SUCC, you make it new node, right? Because you are inserting the new node and you mark it as false and false. And false and false is basically, is the new node deleted? No. Is the new node marked as deleted? No. Continue. Int level is equal to bottom plus 1, level is less than equal to top level, level plus plus. So starting from the bottom level till the topmost level, while true, you are again just uh, taking the predecessor and successor value, and we now have to make new connections, right? So pred dot next level is equal to pred dot next at any particular level is basically is equal to new level if the current next pointer was SUCC. So if pred dot next was pointing to SUCC, it will be new node rather than SUCC because we have to insert the new node. And then at last, you break. And then after everything is done, you do another find search so that you can update the whole predecessor and successor array again because we want to keep the data fresh. So this is add, and then let's go to the remove. This is getting real long. Anyway, so obviously we initialize bottom level as 0, we create our two arrays. While true, this loop goes to infinity till there is a break because in the log free implementation we have to just keep checking whether we get a chance to do what we intend to do or not. Boolean found is equal to find again. We do a find element, a find search, and we fill our preds and successes array. These two arrays we fill. If not found, if the element is not there, then you just return. We can't remove anything else. We uh, we keep the node to remove in node to remove variable, which is SUCC bottom level. So predecessor is the node which is just less than the value we are trying to delete, and successor is whatever predecessor is pointing to. So this will be basically the node to remove. For int level is equal to node to remove dot top level. So we start from the top level of the node to remove. So let's say this is the node to remove. Wait. The diagram is not the most cleanest, so I'm not showing you through the diagram, but okay, let's try. So let's say we want to delete 5. So we start from the topmost. And wait, yeah, and then we create another marked array, right? To just so let's say if I create a marked array, marked, I'll create it marked. So it creates a marked array like this, and at each level it says whether this pointer is marked, whatever this value is it marked as deleted? Is this marked as deleted? Is this marked as deleted? And once all are marked as deleted, we can finally remove this particular node. Okay, this is what marked array is. SUCC is equal to node to remove dot next level dot get marked. So SUCC is node to remove dot next level. So node to remove, this is the node to remove, 5 is the node to remove dot next at this particular level, this dot get marked. So it is fetching the reference to whatever it is pointing to, and plus it is dot get method. It is not just get reference. So and it fills the marked first position as whether the value it is pointing to is marked for deletion or not. So if the value it is pointing to is marked for deletion, if this is true, it will just move on. If it is already marked for deletion. Else, if it is not marked for deletion, we have to mark it for deletion until we succeed. So node dot to remove dot next level dot attempt mark. We attempt to mark it as true, that yes, we want to delete this. We want SCC to be true. And then we check SCC is equal to node dot to remove dot next dot level dot get marked. And so we mark it, and then we check whether it is marked for deletion or not. We do it again and again till it is marked as true. Now, after we have successfully marked it as marked to be deleted, and we have marked all these elements to be deleted because this was starting from top level and going till bottom level plus one. So we have marked every node from the bottom till the second bottommost to for deletion. SEC is equal to node to remove dot next bottom level dot get marked. So we mark the last most bottommost level as for removal as well, and we get whether it is already marked for um, deletion or not. While true, I marked it is equal to node to remove dot next is equal to. Now we are setting it as node to remove dot next. So 5 dot next, we are setting it as SUCC. So whatever SUCC was, we check is it SUCC. If it is SUCC, then we set it as SUCC. So what this means is that we don't need to we are not trying to put any value, right? We are just seeing that whether the value that we have, the next value that we have, is it successor? If it is successor, then great. But if it is not successor, then I marked it will get a false. And if it is false, Boolean I marked it is false. If it is false, then we just return false, right? This is what it is. And so we are checking whether it is successor or not. If it is, then we mark and we check is it marked as false. If it is marked as false, false means is it marked as not currently deleted. If it is marked as not currently deleted, we mark it as deleted. SUCC is equal to SUCC bottom level dot next bottom level dot get marked, and then the successor SUCC will become whatever success is pointing to the next. Okay. And we do this because it might be that the next element that we are trying to get might be marked for deletion. So we have to do this till the next successor is not marked for deletion, and then the moment we find an element which is not marked for deletion, this next element which is not marked for deletion, we mark it for deletion. We mark this particular thing for deletion. If I marked it, if this is true, I marked it. If whatever we are trying to do, we are trying to mark it for deletion, this particular element. If it is true, if we're successful, then we just update the threads and success, these two arrays, and then return to that, okay, this was deleted. Else, if mark 0, okay, marked will have what? SUCC dot next. Were you able to mark SUCC dot next as, sorry, node dot to remove dot next as true? If we were able to do this, then this will be true and we'll return false. So this was the whole explanation for skip list under concurrency. I hope you liked it. This was my first attempt at going through research papers in high performance computing and AI. And the two, I'll mention all the references to different research papers in the comments. Sorry, in the description. And if you guys want to connect with me, you can connect with me on LinkedIn. The link will be in the description. I am, as I said, interested in AI and high performance computing. I love competitive programming as well. I'm not very good at it, but I give it a shot. And take care.